Hi, my name is James Cunningham and I'm going to take you through the Section A higher level on the DCG 2015 exam paper. Okay, so as you see with the Section A you have 4 questions and you have to answer any 3. Alright, so for this tutorial I'm just going to take you through the questions one by one from 1 to 4 and explain step by step how to complete those questions. Okay, we're starting with question A1. The 3D graphic below shows a display box for chocolate eggs which is based on a truncated prism, as you see the 3D image here. Drawing below shows the incomplete pictorial and orthographic projection, so these 2 drawings, of the square base prism which has been cut by the oblique plane VTH. So you can see the traces of the plane here that are actually cutting the solid. Part A of that question, on the orthographic projection on the right, complete the plan and elevation of the cut prism. Okay, so you see the plan here in place and the elevation here, the light blue line to outline the prism itself. First thing I'm going to do here, I'm just going to label that. So I'm going to label 1, 2, 3, 4. So label the corners. Right. So up here on the elevation you have 1, you have 2 here which is a dashed line, 4 which is this line at the front corner, and corner number 3. Alright, so as you can see the question, if you like, or the elevation is partially completed there. So you can see corner 1 brought directly up from the plan. Corner 2 in this case as well. So what we do in this situation is, as you see here with corner 2, okay, because they're being cut by this oblique plane, you're going to bring your points parallel to the horizontal trace and straight up then until they hit the vertical trace in order to locate the height, and then you're going to project them across here again to line up with the corresponding point from the plan. Alright, so we have in this case we have number 2 complete, number 3 is complete here as well. So I'm just going to carry on and do number 1 and corner number 4. Okay, so I'm just going to project those up again. I'll use the red pen as well just to keep it the same as what we have, and I might even do these in a dashed line just to show the ones that we're completing ourselves. So I'm going to bring that point number 1 up until it hits that. While I have my sliding set square set up, I'm going to bring number 4 as well. So remember, we're transferring the points in plan parallel basically, so we're going up in this direction, transferring them parallel to the vertical trace here. Okay, so one by one then going to project up, or number 1 directly up until it hits the vertical trace, and then you're going to bring it across to hit the corresponding line on the elevation, which is this point here. Okay, so I'm going to do the same thing with the corner number 4. Project that up until it hits the vertical trace and project it across onto the corner number 4 in elevation, which is this blue line here. Okay, so now we have point number 1, point number 4, we have 3 already up here, and we have number 2 also. Okay, so I'm going to bring the corresponding corners, I'm going to join those up, and you'll see the cut solid in the elevation view then. Alright, we have number 1 to 2. Number 3 to 4. Sorry, 3 to 4 here. And bring number 4 and 1 as well, so we're going to join those up. Okay, but that then, if you want to shade it in, that's showing you the cut solid there as you have it on the view from the elevation. Okay, the same cut solid as you're going to look down here.
You could buy a pair of rosary beads or get your candles blessed.
So again, no harm to use the different colours just to make it stand out that bit more for you and to make it, I suppose, visually more easy for you to understand. Okay, so that's your cut solid basically for the part A. On the orthographic projection on the right, complete the plan and elevation of the cut prism. So moving on to part B, complete the pictorial projections of the cut prism. So you have the pictorial view here. It basically asks you to complete the projections of each point as you have done here on the pictorial view. Okay, basically what you want to do is label it if you like the same. You don't have to label it, but it just might make it that bit easier for you. So you can just basically project your points as you have done here. To go through that, same thing as you've done here from the plan view. So we have our traces here. We have vertical trace and our horizontal trace. You have the XY line here where the two planes meet, so your vertical plane up here and your horizontal plane. We know from looking at that the plan view is going to be on this horizontal plane, so that's going to correspond to the plan view here. Okay, and what we did here, transferred each of the corners that we needed to complete parallel to the horizontal trace. Okay, we projected them up perpendicular then from the XY line, hit the vertical trace, and then across to the corresponding points on our 3D view here. Okay, I'm just going to complete those. I'll do the first one here and I may speed it up a bit then just to fast forward on to the next bit. I'll project those points across until they hit the XY line. I'm going to project that up vertically then to hit the vertical trace, and again I'm going to project it across from there parallel again to the horizontal trace until it crosses this corresponding point, which you see here. Okay. And just put little arrows there on the direction just to make it easy for you, and so on. Now we have this corner here, which would be your number 1. This guy here at the front is number 4. We have number 3 at the back and number 2 in this corner. Right, we have point 1 and we just need to find the other point. Sorry, we have point 2 here. We have point 3 up here, so now I need to get point number 4. 18,000 feet of runway is an awful long way to go. Again, I'm going to put the arrows on those, give you a bit of direction, and just the points there. I'm going to join back those again just to show you where the 3D, the view where the cut solid is in this situation. There you go, you see the shaded area in this situation, which will correspond to these views here on your cut solids and the elevation and plan. So you have the cut surface on your 3D pictorial view there, which completes the part B of the question. So moving on to part C, on the orthographic projections on the right, so these views here, determine the true inclination of the shortest diagonal of the cut surface. Okay, we're going to look here, the shortest diagonal, and I'm just going to put that in a different colour just to make it stand out a bit. So I'm going to put that in a blue colour, first of all, in both views. So we have the shortest diagonal here, which we can see is from corner 2 to 4. And just to mark that in plan as well, corner 2 and 4. Alright, so again, just determine the true length of the shorter diagonal of the cut surface. Okay, so we see them here in both views. So essentially what I'm going to do is here from point 2 and 4, I'm going to rotate that around until it's on the horizontal, if you like, in line with the XY. I'm just going to draw a light line across here. And because we know when I rotate that around, okay, and project it up, we're going to be looking at the true length in the elevation. Alright, I'm going to rotate that arc around, project the line up, and just put the little arrows in there. This is going to be the line looking at plan view. Alright, so swinging number 4 around to this point, project that up and bring it out where it crosses, or sorry, from the height, as you see it here, from number 4 in the elevation, where that crosses here, that's going to give you the true length. You join it back to number 2. Okay, I'm going to draw that line in 2 to 4. That is going to give us, as we're asked, the true length of that line. Again, that could be completed. Instead of rotating from number 2, we could also rotate here from number 4 and bring number 2 down, which will essentially give us the same result, just to make sure we bring it down onto a horizontal position here where it's running parallel to the XY line. So all in all, that's that question complete. So now we're going to move on to part 2 of that section A. Question 2 here, you can see, involves the parabola. So just to read through the question first of all, the graphic below shows the trophy for the FIFA World Cup. Okay, so you see an image of that here and a drawing. The small outline elevation, which is also given, shows that the trophy is based on 2 identical parabolic curves, AB and CD. So you have AB and CD here. The circle shown is tangent to the curve, so the circle here within that trophy, tangent to both curves. The drawing on the right shows the incomplete outline elevation of the trophy. This is basically what we're working on. We have the incomplete drawing and we're going to progress with that in a minute. So part A, V1 and V2, so you have your vertex 1 and vertex 2 are the vertices of the parabolas, and F1 and F2 are the focal points as given there. Okay, we're basically being asked to draw the parabolas, show clearly how to determine the position of the points B, D, P and Q. So B, D, P and Q. Okay, so first of all, we're just going to carry on with the parabolas. We have our vertex here and a focus. Okay, so we'll worry about the parabolas first and then we'll move on to the points B, D, P and Q. Alright, the first thing I'm going to do, again when it gets starting on the question, is just to work on our rectangles here for the parabola. So as we normally do, we divide the side into, we'll go with 5 equal parts here, and also do the same with the top, and we'll join those to the corresponding vertex and complete the parabola. Okay, so now I have my 5 equal divisions on both sides of the rectangle here. So I'm just going to go along and I'm going to join those up to the corresponding points and locate the points basically on our parabola. Okay, I'm going to transfer them down here below the axis then, and we'll progress from there. Okay, so I have my few points here along the parabola, so I'm just going to plot those and draw a part of the parabola in position for now. Just going to join those points, nice continuous gradual curves there. Okay, so for the following few, as we know, I'm just going to, instead of having to divide our rectangles again, I'm going to project those points down, and I'll measure same distance the far side of the axis in order to plot those points, and likewise I'm going to bring them across as well and do the same thing after that. So now we have here, we have both our parabolic curves on both sides, and after transferring the points across and measuring the same distance from the central axis, both to the left and right and from the top to the bottom of the axis. Okay, so now on to the second part of part A, if you like. So show clearly how to determine the position of points B, D, P and Q. Okay, so point B and D here at the bottom, they're basically where the parabolic curves are intersecting with the ground, if you like. So this is point B, over here on the opposite side point D, and to project those directly up then, if you like, project those directly up here to where they hit the curve on the top, same on both sides, and that'll give you point P here and point Q on the other side. Okay, so that's all in all, that's part A of that question 2 complete. Right, so moving on here to part B. Draw the circle tangential to the curves at point P and Q. Okay, so we have point P and Q here. I want to draw a circle within that area that is tangential to both curves at those points. Alright, basically what we do in that situation is we join our focus point here on either side, if you like, back to point Q. Okay, so our focus point back to Q. We're just going to draw a horizontal line here up towards the central axis here, if you like. Okay, that horizontal line, that's going to give us here is an angle between the two lines which we're going to bisect in order to get the tangent line to point Q. Okay, so just bisect that angle. Why do we need a tangent? Well, we're just going to use the tangent in this situation. Okay, just going to use the tangent here in order to give us a line to work perpendicular off, and that in turn will help us to locate the center point of the circle we're looking for. Okay, so the tangent in this case is from point Q through this bisector. Okay, so that's our tangent line there. And now if we work perpendicular off that tangent line, okay, perpendicular off that tangent line from point Q here, and that is going to give us our center point then, where it hits the central axis, giving us the center point for that sphere or that circle. And you can just check that then to make sure it's accurate, that it's running tangential to point P and to point Q. Okay, I'm just going to shade that in just to give it a bit of, visually give it a bit of a lift. And again, that's your question 2 on that section A complete. So question 3 on this paper is in relation to laminar planes. Okay, So just to get straight into it, the 3D graphic below shows a sculpture based on intersecting planes. So you have the graphic here. The drawing shows the elevation and plan of the two intersecting planes, ABC and ADE. So you have your elevation here and your plan down here. Okay. Part A. Draw the plan and elevation of the line of intersection and determine the dihedral angle between the planes. Okay, so first thing up here is to get the line of intersection between the planes ABC and ADE. Alright. For that part, it's actually quite simple here. So we can see, I'll start here with our elevation that points D, B, C and E are on the ground, so they're all at the same level. We have B, D, C and E here. Okay, so where those planes intersect here, we know that this is giving us 1 point on the end of the line of intersection. Okay, and the common point to both planes here is point A. Alright, so that means that this line here in plan from point A down to the intersection here of the line DE and BC, and just to join those 2 points up, and that's basically giving us our line of intersection in the plan. Okay. And of course, to locate that in elevation, well, we already have the common point A here, so I'm just going to bring this point of intersection, the other end of the line of intersection, up. Okay, and of course where that hits the XY line, that's giving us our point to join back to A, and that in turn is giving us the line of intersection in both your plan and the in view. Alright, so again, another part to that was to determine the dihedral angle between the planes. Okay, so the dihedral angle between the planes ABC and ADE. Okay, so for this part you can take an auxiliary view basically of the line of intersection. Now this can either be done from the plan or from the elevation. Alright, so based on the space you have around the sheet, you can decide on which of those to take. The only difference there is if you take it from the plan, you'll be measuring your heights of the 2 points in the elevation, and vice versa. If you take the auxiliary off your line of intersection from the elevation, you're taking your heights from the plan. Okay, so in this case I'm going to actually take it from the line of the line of intersection in the elevation. Okay, so I'm going to project my points across 90 degrees to the line of intersection. Base points I'm going to draw my x1, y1. Alright, so this is my x1, y1. So taking the points ABC and ADE basically across from that. And for this again, instead of measuring down from the XY line here, okay, because if I'm measuring down the XY line, which I can, it's not a problem, but it means if I'm measuring from the XY down to these points, it's going to push it further down the sheet. Okay, so I'm going to insert a datum line there from point A. Okay, so I'll call that the datum, and basically that datum is a reference point for taking my measurements. Okay, so instead of measuring down from the XY line, I'm going to take my measurements now off each point from the datum line down, and I'm just going to join the points directly up there just to make sure we're 100% accurate with that. Okay, so starting with point D here from the outside, taking the measurements down, I'm going to plot the points. We have our triangles ABC. We know point A here is on the ground because we're measuring from here. So I'm going to join A, B, C. and I'm going to join ADE. Okay, so that's giving us our two triangles here. Sorry, yeah, I have that correct. That's giving us our two triangles there. We have the line BC and ED here, similar to having BC and ED. And that's going to give us our line of intersection up through that also. So I'm just going to draw that in there, the line of intersection, the dashed line. Okay, so essentially what we need to do now in order to determine the dihedral angle is to get another auxiliary view of this line of intersection. Okay, so I'm going to project down another auxiliary view down there, plot the points once more, and that then will give us our position of the laminar planes from a point view, which will allow us to determine the dihedral angle between them. Okay, so here I have my x2, y2, so we're looking down along here, projecting our points A, B, C and A, D, E down along there. Sorry, I just forgot to bring the point A actually. I'm going to project that down as well. Alright, and when we're dealing with auxiliary views, you always take your measurements basically from two views back. So this is the view you're working on. So we'll go back two views, and we'll take our measurements from that. Okay, so in this case, I'm going to be measuring back here, and we'll plot the points again. Now with my points plotted, basically what I did there was, I'll just draw that in a different colour, our line of intersection. Okay, we did a second auxiliary view, looking along the line of intersection. Okay, we projected our points down, so A, B, C and A, D, E, and we can see that point A here is common to both lines as it appears on this auxiliary. So this is our triangle ABC, or the laminar plane ABC as it appears looking from the point view, and this is the one ABD. Okay, you can see I'm slightly gone down over the next drawing there, but you can see that there. And you can take your dihedral angle then between the two planes. Okay, and this here be your dihedral angle. Alright, so remember part A was to draw the plan and elevation of the line of intersection, which we did, and determine the dihedral angle between the planes. So the dihedral angle consists of two auxiliary views basically, which we did here. So 1, 2, and got our dihedral angle there. So moving on to part B, determine the traces of the plane ADE. Okay, so the traces of the plane ADE. I'm just going to colour that plane in a bit there, just to make it stand out a bit more for it. So in plan here we have A, D and E. So just to colour that one in a slight bit of shading, just to make it visually a bit easier to see which plane we're dealing with. Okay, so we can see from here that we are working off the plane ADE, and we're asked to determine the traces of the plane ADE. Alright, so we see the plane ADE shaded in green. We know that the laminar plane, or the portion of that plane ADE, is sitting at ground level here, because we see that from the elevation. Okay, so if that's the case, sitting on ground level, well, the horizontal trace is where the plane itself intersects the horizontal plane. Okay, so where the laminar plane intersects the horizontal plane, and we know from this that that is along the line DE. Okay, so that's essentially the line DE. When you extend that on, that is your horizontal trace. Okay, so that's your HT. Okay, next part, for finding our vertical trace, we need to find another point that is common to that partial plane. Okay, so the green triangle here, ADE. So we know the top point here is point A. Okay, so working off that oblique plane, or the plane that we're looking for the traces of, we need to bring point A up towards the XY line. Alright, and the way we do this is you actually bring it, because it's on the same plane, okay, you bring it parallel to the horizontal trace until it hits the XY line. So bring it up there parallel to hit the XY line. So project that up from the XY line, project it up vertically, and transfer the same point, which is the point A. We need to take the altitude or the height from that, from the elevation. Okay, and where those 2 points intersect, that essentially, that's giving us another point on the vertical trace. So now we have one point here where it meets the horizontal trace, and the other point on top. So that is that part of the question finished. We have our vertical trace, and down here we have our horizontal trace. So moving on to the last question, which is question 4 on the 2015 higher level section A. And this question 4 is working in relation to skew lines. Okay, so you see the skew lines here, A, B, C, D, both in the elevation and the plan view. Alright, the graphic below shows the Durry Peace Bridge, which contains 2 inclined pylons supporting the cable structure. So you can see the pylons here supporting the cables. The 2 pylons are represented by the skew lines AB and CD on the right. Part A of this question is asking you to determine the projections of the shortest horizontal line between the 2 skew lines. Okay, so a horizontal line here somewhere between those 2 that will be at its shortest distance. Okay, so working with skew lines, basically we need to kind of to transfer one of those lines AB into a part of a plane essentially. And the way we do this, if you remember back to the skew lines topic, is you pick a point on one of those skew lines. So B in this case I'm going to pick, and we have to draw a line parallel to CD from that. Okay, first of all what I do here is I draw a horizontal line from point A in this case. So you can pick whatever point suits best for the space on the sheet. Okay, and then I'm going to bring a line from point B, which is the other end of that line, up to intersect that. So point B parallel to the line CD. I'm going to project that up here. Okay, so this point X here, I'm going to call it where these 2 intersect. Alright, we're going to form a portion of a plane. Right, so that's the elevation of that. Essentially, to find that in the plan view, we're going to do the exact same thing. Alright, so I'm going to project down that point X. So from B here, we projected a line parallel to CD. So I'm going to do the exact same thing here. So from B, I'm going to draw a line parallel to CD. So this point of intersection here is point X, and as you can see from X here, it comes back through point A. So I'm going to join that up there to show the full plan view of that laminar plane ABX in this case. Okay, and what that gives us is the true length line, which is known as our strike line. So true length, and true length up here. And getting back to the question, determine the projections of the shortest horizontal line between the 2 skew lines. Okay, so I'm going to now do, if you like, an auxiliary view of that, and that's going to give us the view that we'll see in a second. Okay, and from that view we'll be working backwards when we get so far on, in order to get the shortest distance between, the shortest horizontal distance between that. Okay, I'm going to take an auxiliary view of that, looking along the true length line. here is going to be my XY. So if you're looking from this direction, project those points out. So as we see the line AB and CD here now, we see what appears as a parallel view, okay? But we know with skew lines, they never actually are parallel, but there always is one view where they do appear to be parallel. Alright, so what I want to do here now is another auxiliary view looking perpendicular to these lines of projection, and this is going to give us an intersection between two skew lines, okay? So you'll see that intersection, and that is where the shortest horizontal distance is going to be taken from. So I'm just going to project another auxiliary view here. I'm going to take my heights again from 2 view back, and we'll take it from there. So here we have the I have the line AB here. Sorry, it's just overlapping a slight bit here, so you just be wary of that, okay? So when we took our second auxiliary, we have the line AB and we have the line D. So now I have, what I've done here is brought an auxiliary of our first auxiliary, if you like, in order to get a point of intersection between the two skew lines AB and CD. So you can see it's slightly overlapping here. So just watch out for that on your sheets when you're drawing. The reason I did that is to get the closest point basically between those two lines. So what I have to do now, if you think back to the question, it asked us to determine the projections of the shortest horizontal line between the two skew lines. So essentially what I'm going to do is to bring that point, which is the closest point on the two lines, I'm going to transfer that point back along parallel to the lines of projection in order to get us the shortest horizontal distance. So remember, if it's the shortest horizontal distance, well then that means that it's going to be parallel to your XY line. So this is actually it here. This is your shortest horizontal distance. Alright, so I want to transfer that now back through all the views. So back to our plan view. So where it hits the line CD, and bring that dashed line back, where it hits the line CD and where it hits the line AB. Okay, and that's going to give us the 2 points for that in plan. Alright, so we'll join the 2 points here to give us the shortest horizontal distance, and again I'm going to project that up to the elevation. So again, where it hits the line AB, project it up. Okay, so just put a little arrow on those, that's your point, and where it hits the line CD. And again, I'll draw that in on the elevation. So that's the shortest horizontal distance. Alright, so that line again should be horizontal there. It's just a slight bit inaccurate in my drawings, obviously. So that'll be your shortest horizontal distance. Alright, so the shortest horizontal lines are between the two skew lines. Okay, and for the last part of that, part B, it asks us to determine and indicate in degrees. So just be cautious with your questions here, that you read them correctly. So sometimes it may ask you to determine, and sometimes, like in this case, determine and indicate in degrees. So that means you have to measure that with your protractor in order to answer the question fully. Okay, so determine and indicate in degrees the true angle between the horizontal line and the vertical plane. So between this horizontal line and the vertical plane. So again, don't get caught out here. You must remember that this asks you to get the angle between the vertical plane, so do not get mixed up with the vertical plane and the horizontal plane. Alright, so we know here the vertical plane, the intersection, which is the XY, will represent the vertical plane as we're looking down on the plan. So basically what we're going to do is carry that line on until it hits the vertical plane, and that will in turn give you your two lines here to measure your angle between them. Okay, when you have that in place, basically all you need to do then to complete that question is to measure that angle and write it in degrees what that angle is. Okay, and that is the full question then, part A and part B complete.